multimeter never met an amp it didn't like. It's going to measure all the amps going into my computer. But my computer's only going to use 60% of those amps. It's going to throw the other 40% away. Now my watt meter knows this. It's only going to measure the amps that my computer uses. This is true power, and this is apparent power. What's going on? The electric utility supplies your residence with AC voltage and current, but some electrical loads convert a percentage of good AC current into types of bad AC current as a byproduct of the equipment's normal operation. Now these bad currents are what cause low power factor. Here are examples of different electrical loads. A 100-watt incandescent light bulb is a resistive load that only consumes true amps and dissipates watts as heat and light. The AC current and voltage are in phase and there is no power factor. A big industrial motor like this one, with its many inductive windings, cause a phase displacement between the AC current and voltage and create additional reactive amps needed to expand and collapse its magnetic fields. These reactive amps do not produce useful watts. Reactive amps are bad. Now here we have a rectifier diode, computer switch mode power supply, UPS backups, and triac lamp dimmers all create wasteful harmonic currents by chopping and distorting the AC waveform. Harmonic currents? Bad. A device has low power factor when it draws more current than it uses. A power factor of 0.7 means that 70% of the amps flowing in the electrical wires produce watts that turn this motor's rotor, while 30% of the amps flowing are reactive amps that produce no watts. A power factor of 0.6 means that 60% of the amps flowing in the electrical wires produce watts that develop operating DC voltages and DC current for this computer power supply, while 40% of the amps are harmonic currents that produce no watts. A power factor of 0.8 means that 80% of the amps flowing in the electrical wires produce watts for this lamp dimmer and light bulb, while 20% of the amps are harmonic currents that produce no watts. A power factor of 1 means that 100% of the amps flowing in the electrical wires produce watts that power this light bulb. Power factor represents the percentage of electrical amperage supplied by the electric utility that actually performs work. Good electrical amps come into your residence, but some of your household appliances are going to trash those good amps into bad reactive amps and bad harmonic amps. The kilowatt-hour meter the electric utility uses to meter your electricity measures the good amps used to produce watts. But it ignores the good amps that your appliances turned into bad amps. Therefore, watts equals current times voltage, where I equals only the good amps used to produce watts. VA is measured using your true RMS digital multimeter, but a digital multimeter cannot distinguish between good amps and bad reactive amps and harmonic amps. It sees all current as worthy. The A in VA is a combination of good and bad amps. The multimeter will naturally measure more amps than the kilowatt-hour meter. If you put the amps measured by your multimeter into the power equation, you're going to calculate an inflated watts. So they gave the multimeter amp its own power equation. Instead of IE, it's VA. And instead of true power, it's called apparent power, because it looks like the extra power is apparently there, but it's not. Only good amps produce watts. The whole idea behind power factor correction is to eliminate the reactive amps and harmonic amps. In the power factor equation, we can see that the voltage E from the true power and the voltage V from the apparent power, they're always going to be equal, so we can just cancel them out. And what we're left with is I over A. Now, when the power factor equals 1, there are only good amps. I is going to equal A. The current from true power is going to equal the current from apparent power. There's going to be no reactive amps and no harmonic amps. This power factor meter also measures watts, VA, and true RMS current and voltage. If the device manufacturer specifies the power factor, you can calculate watts by using a digital multimeter to measure the volt amps, and then multiplying that times the power factor. A light bulb is like a simple resistor. In a resistor, the current amplitude is in phase with the applied voltage. I'm going to plot the power curve by taking the instantaneous current and voltage amplitudes along the sine wave. I'll take the current here and the voltage here, that's the maximum instantaneous. This would be 0. And since this is a negative current and a negative voltage, you multiply them together and you get a positive. So I'm going to plot the power curve. It's always positive, and the resistor is always dissipating true power or watts. You can see that there is no sine wave distortion. That means that there are no additional harmonic currents. And there's no current or voltage phase displacement. That means no additional reactive currents. A light bulb has no power factor. An AC motor has many turns of wire around the armature that are needed to develop a strong magnetic field to turn the rotor. The looped wires form an inductor that shift the phase angle between the current and the voltage. When amps flow into the motor's windings, the magnetic field expands and stores electrical energy. When the field collapses, the amps are forced back into the source. These are the reactive amps. Notice that the total power dissipated is 0 watts. To stop the reactive amps from flowing in the electrical wires, a capacitor is placed in parallel with the motor. The reactive amps now flow back and forth between the capacitor and the motor. This resonance prevents reactive amps from flowing in the connecting electrical wires. To correct the motor's power factor, a parallel capacitor was needed to bring the current and voltage phase displacement back into alignment. That just won't work with a computer switch mode power supply. Here's the input bridge rectifier and filter capacitor to a switch mode power supply. This circuit converts the residential AC into a high voltage DC that serves as operating voltage for this switching transistor. It's this bridge rectifier and filter capacitor circuit that caused the low power factor in a computer's switch mode power supply. I'm going to measure the AC residential voltage here on channel 1 of my scope. This shows a nice 60 Hz sine wave. Here's the spectrum analysis showing a single 60 Hz sine wave fundamental. I'm going to put my current probe on channel 2 right here. These current spikes are caused by the bridge rectifier when charging the DC filter capacitor. This is what produces the harmonic currents. Whenever an AC sine wave is distorted, AC current is redirected from the 60 Hz fundamental into these harmonic frequencies that produce no useful watts. They only heat up components and cause electromagnetic interference. Now I'm going to add the power factor correction circuitry between the bridge rectifier and filter capacitor. This integrated circuit chip controls the transistor, which affects how current flows back and forth between the inductor and filter capacitor. This has the effect of smoothing out the charging current waveform. The IC is able to realign any phase shift displacement between the current and voltage, and it also produces a nice sine wave current having no harmonic components. Here's the pseudo sine wave from an uninterruptible power supply. This is during an electrical outage when my UPS is on battery backup. Notice the distorted AC sine wave. It's like they built it from a bunch of square waves. This is where the actual sine wave is. Right here. By distorting the AC sine wave, these harmonic currents are produced. And this is what causes the low power factor in a UPS backup.